Okay, bright enough. Hi everyone, I am Dharmik. I work as a software engineer at ARM. I have been working on DPDK since more than a year now. And today I'll be presenting on a comparison between hardware transactional memory and lock-free algorithms. As the number of CPU cores in a single SoC increase, scalability becomes really important. And these mechanisms help improve scalability and speed up execution of a multi-threaded algorithm. So it becomes really important to take a close look at these mechanisms. DPDK is in a unique position because within DPDK we have the RT hash library, which implements an optimized hardware transaction memory based solution as well as a lock-free solution. So I'll briefly introduce you to implementation of RT hash within DPDK. Then we will look at a couple of read-write concurrency problems within the hash library and what solutions are implemented in order to support read-write concurrency. Moving forward, I will talk about basic working of hardware transaction memory and some scenarios wherein hardware transaction memory fails. And then I'll talk about lock-free algorithms from a software developer's perspective. Then we will look at performance comparison of these three solutions. And I'll conclude my talk with mentioning some of the challenges that software developers face when working with hardware transaction memory and lock-free algorithms. So let's begin. So RT hash uses cuckoo hash algorithm in order to resolve collisions. And how it does this, I will explain shortly with an example. But before that, this is what the implementation looks like. We will go from left-hand side of the screen towards right. So we have the hash function, which translates the input key to signature and alternate signature. And from these signatures, we derive bucket indices. And a bucket index points to a location, which is an array of 8 buckets. Within each bucket, we have the key index stored. And this key index is pointing to a location in the key store array where the actual key and the application data is stored. So the key point to remember here is that a key can fit into either of two locations, either the primary bucket or the secondary bucket with the cuckoo hash implementation. So let's see what happens when there is a collision. So this is the hash table, and we can see that 3 out of 4 buckets are completely filled, and one of the buckets is fairly empty. Let's say there is an incoming key equal to Z, and the primary and the secondary bucket for this particular key are completely filled, so we have a collision here. So what cuckoo hash does is, it tries to shift keys around to their alternate locations. We saw in the previous implementation that a key has a primary location and an alternate location. So a writer will try to shift keys around to their alternate locations to see if it can accommodate this particular key. So let's say it has implemented the shiftings behind the scenes, and it has come up with this particular pattern of shifting the keys in order to fit key Z to its primary bucket. So I's alternate bucket is fairly empty. So it shifts key I to its alternate location. So it moves from primary bucket to secondary bucket, which makes space for Q in its alternate bucket. So now key Q can move from secondary bucket to primary bucket, which further makes space for D to move to its alternate location. And with the movement of D to its alternate location, we have space for the new key Z in its primary bucket. So this is the way a writer resolves collisions. And the most important thing to note here is that keys are being shifted from primary and secondary buckets back and forth with cuckoo hash implementation. And this becomes really challenging when implementing lock-free algorithms. I will reiterate this when I talk more about the lock-free implementation. Okay, so yeah. So let's look at a couple of read-write concurrency problems within the hash. So here we have the hash table, which has a couple of keys stored. One is key equal to 1, which has no data or null data. And the other key is key equal to 5, which has data equal to E. Both the keys are residing at key indices 100 and 105 respectively. So let's say we have a reader R1 which would like to look up key equal to 5. So it finds the key in the hash table, but before it could completely fetch the data, it gets blocked. In the meanwhile, another writer, writer 1, would like to delete this key. And since there is no communication between the readers and the writer is unaware of the fact that there is an active reader on that key. In an ideal situation, a writer has to wait for all the readers to finish before it can modify the hash table. So it finds the key in the hash table and it deletes it. And it releases the key index so that newer keys can reside in those locations. Now the reader wakes up, it is unaware of the fact that the key has been deleted, and it successfully fetches data from a deleted key. So the problem we saw here is that writer might modify or delete a key that is currently accessed by a reader. In another scenario, we have a writer W2 which would like to update data for key equal to 1. So it finds the key in the hash table, and before it could successfully modify the data completely, it goes to sleep. In the meanwhile, another reader, R2, attempts to look up that key. Now, there is no synchronization or communication whatsoever between the readers and the writers. So, reader R2 will look up that key and it will fetch the incomplete data. In an ideal situation, readers have to wait for writers to finish modifying the hash table before they can look up keys. So the problem, and now the writer wakes up and it will update data for key equal to 1. So the problem we see here is that readers might look up inconsistent data while a writer is currently updating it when there is no communication between readers and writers. So let's see how RT hash solves these problems. So we have 3 solutions within RT hash. One of the basic solutions is using traditional read-write lock, and most of you might be aware that a traditional read-write lock allows concurrent read accesses and exclusive write access. A more advanced and a better performing solution is transaction memory read-write lock. So what it does is it tries to execute critical section in a hardware memory transaction. And what I mean by that, we will see in the next slide when I talk more about hardware transaction memory. But the catch here is that if the transaction memory support is not available, or if transactions fail, then it will take a slow path. It will use the traditional read-write lock. So in what scenarios a transaction would fail, we will see in the next slide. And another solution is lock-free readers. So this solution was introduced by Honapa last year during the Dublin Summit. And with this implementation, the readers are lock-free, which means they are not blocked by an active writer, as is the case with the traditional read-write lock. So there is no communication between readers and writers here. So it is interesting, in the previous slide we saw that the read-write concurrency problems arising because of the lack of communication or synchronization between readers and writers. But here we have a solution which supports read-write concurrency with this lack of communication. So how it is being made possible, we will see when I talk about the lock-free algorithms. But this solution works really well when the writers are operating on control plane, where the probability of a writer getting blocked is high. In such a situation, read-write logs, they don't perform really well because a blocked writer will prevent readers from looking up the hash table, and in that case the lookup cost will be really high. But with lock-free readers, there is no such problem. A blocked writer will not prevent readers from looking up keys from the hash table. Okay, so hardware transaction memory. Intel has support for hardware transaction memory in its architectures, and even ARM has announced support for hardware transaction memory in future architectures. So it becomes really important to take a closer look at this technology. So what exactly is hardware transaction memory? What is it aimed at achieving? So hardware transaction memory is aimed at achieving concurrency without locks when CPUs are operating on separate memory addresses, cache lines to be precise. So let's say we have a scenario within hash that a reader is looking up from a bucket that is different from the one writer is trying to modify to, or let's say we have 2 writers which are modifying 2 different buckets. In such a situation, there is no data contention whatsoever, and you don't need read-write logs in order to support concurrency. All the CPUs should be allowed to work or operate concurrently. But with traditional read-write logs, that is not the case. One CPU will block other CPUs from accessing the hash table. But with hardware transaction memory, what it does is it speculates that you can perform atomic operations over multiple cache lines. The word speculate is really important here because it doesn't know for sure if the atomic operations will be successfully performed, but it just speculates that it will perform atomic operations. It can result in a failure, and in case of failures, it will take a slow path. So what hardware transaction memory does to implement this is it uses the existing cache coherence protocol. It can be any protocol, MESI, MSI, etc. And it adds tracking information to the cache lines. So let's say you are executing a transaction. A transaction is nothing but an isolated, an atomic sequence of memory accesses. So within a transaction, all you have to do is you have to track whatever cache lines you are reading or writing to speculatively, and that is all hardware transaction memory does. So what can lead to a transaction failure or a success? So let's say you are in a transaction, you are tracking all the cache lines, and at the end of the transaction, if you are able to successfully track all the cache lines, which means throughout the transaction, all the cache lines are sitting in your cache in a state that is okay, then the transaction succeeds. The term used is transaction commit. So whenever a transaction succeeds, to all other CPUs, it appears that all the memory writes have appeared atomically. However, if you are not able to track any of the cache line during a transaction, then the transaction fails. It is termed as transaction aborts. So let's say if during a transaction, if a particular cache line you were tracking, which means you have speculatively read or written from, if that cache line moves out of your cache or it changes its state, then you can no longer track that cache line and the transaction fails. So what are some of the reasons why a transaction could abort? So one of the reasons is coherence requests from other CPUs. So we have three kinds of conflicts here. So let's say you are in a transaction, you have speculatively read from a cache line as a part of transaction, and it is sitting in your cache in a shared state. And now other CPU would like to modify that cache line. So the state needs to be changed from shared to exclusive. In such a situation, you can no longer track that cache line and the transaction has to abort. In another scenario, let's say you have speculatively modified a cache line and it is sitting in your cache in a modified state, and let's say some other CPU would like to read or write to that cache line. In such a situation, the state needs to be changed from modified to shared in case of read-write conflict, or modified to exclusive in case of write-write conflict. And again, you cannot track that cache line anymore, and the transaction will fail. Important thing to note here is that there is no such thing called as a read-read conflict. So let's say you have speculatively read from a cache line and it is sitting in your cache in a shared state, and other CPUs would like to read from that cache line. So it can sit in everyone's cache in shared state and there won't be any conflict, and the transaction won't abort in such a situation. One of the most common reasons for transaction failure is hardware limitation. So this has something to do with the way caches are designed. So for an 8-way set associative cache, you have a pattern of 9 addresses which cannot altogether fit in the cache. So let's say if your transaction comprises of the wrong 9 addresses and 8 of them are sitting in the cache, the 9th one will evict one of the cache lines and you can no longer track it, which will result in a transaction failure. So the 32 kilobyte might not be the pure capacity of the cache. And another common reason is anything that isn't memory. For example, interrupts, hardware I/O system calls will result in transaction failure. So if you are in user space and if you do a context switch to kernel space to take a system call or a trap, then it will result in transaction failure. Okay, lock-free algorithms. So what a software developer needs to know when making an algorithm lock-free. So first is identification of payload and guard. Payload is the data being propagated from writer to reader. So in case of hash, payload can be thought of as the key that is stored in the key store array. That is the payload. Accesses to the payload need not be atomic because it is being protected by the guard variable. So what is a guard variable? In case of hash, the key index that is stored within the bucket that is pointing to the key is the guard variable. So what applications or what writers do is they first modify the payload non-atomically, and then they atomically update the key index. And readers on the other side, they atomically first access the key index, and if they have a valid key index, they are guaranteed that it will point to a valid key. So that is the idea here, or at least that is how the lock-free algorithm is implemented within RT hash. So naturally we need atomic operations for guard variable because you don't want broken writes or reads to the guard variable or the key index, because broken writes or read to key index will lead to an inconsistent key. And the last important thing that developers need to keep in mind are the memory ordering operations. So you need memory ordering operations because you have designed your algorithm in such a way that, for example, first you will update the key and then you will update the key index to the application. If that sequence is broken, maybe because of the reorderings that compilers like to perform, or even the architectures perform reordering in order to improve efficiency, then the algorithm will break. So for example, let's say you have partially modified the key or the payload, and then you update the key or you expose the key index to the applications, then readers can look up a valid key index, but they will not have the consistent data. So memory ordering operations are really important here to ensure that the guard is truly guarding the payload, and these include the load acquires and the store releases. Let's look at performance comparison of the three solutions. So here we have the lookup cost with 0% writes, which means there are no concurrent writers. And this is for single lookup. So we see here that the traditional lock, which is in red, is not scaling really well compared to other two solutions, while hardware transaction memory based solution and the lock-free solution, they are scaling really well with increase in number of readers or the cores. And lock-free solution performs really well in this particular scenario. For single core, we see that hardware transactional memory imposes a significant overhead. So we can see the lookup cost for hardware transaction memory based solution, which is in orange, for single core is significantly high compared to the other two solutions. Now when we include a writer, the trend more or less remains the same. The hardware transaction memory based solution and the lock-free solution, they are scaling really well, and the performance degrades even further for the traditional read-write locks. With bulk lookup, even though it might appear that the lookup cost is high because the bars are taller than the previous graphs, but the y-axis scale has changed now. Bulk lookup performs really well, significantly better than the single lookups. This is because with bulk lookup, a reader can look up maximum of 64 keys at once, which means that the number of times you are acquiring or releasing a lock has significantly reduced now. But again, like when we include a writer, a concurrent writer, or beyond for 4 or more cores, the performance with traditional read-write locks degrades. However, the other two solutions are still scaling really well. And this is the last topic for today. Like what challenges do software developers face when working with hardware transaction memory and lock-free algorithms? So first, let's look at the hardware transaction memory part. First challenge is that it requires code refactoring in order to keep critical sections small. This is important because smaller critical sections ensure that the transaction size is small, which means higher probability of transaction success. Also, small critical sections ensure that the transactions execute fast, which means less probability of transaction failure because of interrupts, system calls, etc. We saw this earlier. It imposes significant overhead during low contention. We saw in the previous graphs that even for single core and pure lookups, which means there is no contention whatsoever, hardware transaction memory did not perform as good as the other solutions. And it cannot be applied blindly. You cannot expect the performance to improve by just applying hardware transaction memory solution to any piece of code. So for example, counters, queues, etc., they always contend. There will always be some CPU which will want to read or write to a cache line that is sitting in your cache in a speculative state in the middle of a transaction. So it doesn't make sense to apply transaction memory based solution here. Also, anything that isn't memory cannot be applied transactionally because the CPU cannot roll back if the transaction fails in such situations. So you cannot apply transaction memory, hardware transaction memory based solution to interrupt system calls, IO, etc. Let's look at some of the challenges with lock-free algorithms. One of the basic is algorithm-specific challenges. Every algorithm is implemented differently, and there is no standard solution in order to make an algorithm lock-free. Every solution is different. I would like to point to one particular challenge that we faced when implementing lock-free solution within RT hash. So we have the hash table, and let's say a reader would like to look up key equal to q from the hash table. So it looks up the primary bucket and it doesn't find the key because the key is sitting in the secondary bucket. But before it could look up the secondary bucket, a writer shifts key q from secondary bucket to primary bucket. We saw this. This is done to accommodate newer keys in the hash table. And the writers are not aware of the fact that there are active readers because the readers are lock-free. Also, readers are not aware of the fact that there are active writers. So we see that the key q has been shifted to primary bucket. Now if the reader looks up for key q in the secondary bucket, it will not find the key. And it concludes that the key is absent or the key is missing, which is not the case. The result is incorrect here because we see that key q is present in the hash table. So there are similar challenges. This particular one was solved by introducing a global counter which writers modify whenever they are shifting keys from primary and secondary buckets back and forth. And readers, they can look up the state of the counter, and if the state has changed, they do another round of lookup. Atomic operations are needed for guard variables. Sometimes this can be 128 bits, and the problem here is that not all platforms have support for 128-bit atomic operations. It is really difficult to simulate all test cases because memory ordering operations are involved. It becomes difficult to write a test case which will perform a particular memory access at a particular point in time. Also, with the challenge we saw, in order to prove correctness of that solution, you need a data set which will move or shift keys from secondary bucket to primary bucket, that too at an exact point wherein the reader is done looking up the primary bucket and it is about to look up the secondary bucket. So simulating such a behavior is very difficult, and that is the reason why proving correctness of lock-free algorithms becomes really challenging. And the last but the most critical challenge with lock-free solution is it has to rely on additional handshaking mechanisms between writers and readers whenever a writer is attempting to reclaim or release a memory. Because the readers are lock-free, the writers are not aware of the readers or active readers. So before it can release or reclaim memory, it has to make sure that there are no active readers on that memory. And that is the reason it has to rely on additional mechanisms to make sure that there are no active readers on that memory. So one way to do it is using read, copy, update mechanisms. And that's about it. Thank you.
Do we have any questions? Thomas over there.
Hi. I just wonder if transactional memory is supported on all CPU.
What is that? Sorry, I didn't quite get it.
Transactional memory. Is it supported in all CPU?
I'm aware of Intel, I think from Broadwell it has been supported. And for ARM, we are expected to have it in the future. It is not supported in all the CPUs as far as I know.
So I don't really understand how it works because when I look in the code, I see that this routines is called every time. There is no condition to call transactional memory.
Yes, so the routine is implemented in such a way that you will see an if-else. If the transaction memory support is available, it will use that. If not, then it will take a slow path, which will use the traditional read-write lock.
So it's trial and failure.
What is that?
It's a trial and failure model.
Sorry,
we try to use it, and if it fails, okay.
Yeah.
Because we may have an issue because maybe we want to disable it for Intel.
Yeah.
Maybe you don't know, but there is a new issue.
I believe there is a flag in the RT hash which you can use.
I don't see it. And in general, I think we need to globally disable this feature in DPDK wise.
Okay. Yeah, I think that is a good idea. But at least in RT hash, if you have support for hardware transaction memory, you can enable that flag and it will take care of it.
Okay. Okay. Are you aware that there is a new bug discovered in Intel CPU because of that? Okay, it's a news from yesterday.
Okay.
Do you have so right now, how much, in terms of your benchmarks, do you have a higher number of contenders for to create contention on the lock?
Yes, I have unit tests for that, but again, that was like, I see sometimes, as I said, the solution will not perform well, like the lock-free solution will not perform well if there are more shiftings behind the scenes because readers are doing more rounds of lookup. So I have a test case for that, but given the time, I could only present one of the couple of scenarios.
We'll follow up.
But we can talk about it. Yeah.
Thank you.
Yes. So you mentioned that ARM came up with the transaction memory support, but what you show here in the slide is one use case where the lock-free algorithm are superior versus the transactional memory. So do you have use case in mind where transactional memory actually perform better versus lock-free algorithms?
Not really. I have not encountered that particular use case, but I believe there should be one. So I shared that lock-free solutions come up with their own set of challenges, and it might be possible that a lock-free solution might not perform well compared to hardware transaction memory, but I am not aware of any such use cases. Sorry. Maybe Honapa can comment better.
Yeah, just to comment on that topic, that's what we were trying to find out, how these two algorithms compare, the transactional memory-based algorithm and the lock-free algorithm. What we are trying to show here is the transactional memory algorithm has got an overhead, and it's information for the hardware engineers to go look at why there is such a big overhead. ARM obviously has announced it in the architecture, but the CPUs are not implemented yet. I would like people to be aware and keep this in mind, that there are equivalent lock-free algorithms. Can we make transactional memory as good as those?
Any more questions? Okay. Thank you.
Okay, thank you.